So welcome back, everybody. And we obviously hope you all had a good break. So I wanted to give you a kind of suggestion for the rest of the semester. And this will also link with the different project possibilities. So you probably, I don't know if you had time to look at the slides. So this week I have two sets of PDFs. One is just the one you're looking at now with the plans for the week. And then there's one which is called Week 11 slides. And this is still due to me not having been able to implement this quantum circuits in LaTeX into a Jupyter notebook. So you will have to suffer this kind of dual PDF setup. Then what we also have are two notebooks with examples on how to implement a quantum Fourier transform. So I'm going to repeat a little bit about the quantum Fourier transform from last week, and then we are going to look at how we can implement it. So as we said, the quantum Fourier transform is a kind of kitchen item which enters, for instance, the quantum phase estimation algorithm, which is the one we're going to look at today. And the quantum phase algorithm is then a basic ingredient for the HHL algorithm, which then is used to solve a linear algebra problem. And the linear algebra problem is matrix A times unknown vector X equal to a known vector B. That's a pretty familiar linear algebra problem, which enters so many applications in science, from the solution of differential equations to optimization problems, etc., etc. And you will see examples of at the end on how these can be linked. So today, what I wanted to do is to say a little bit more about the QPE so that you get a more basic feeling of it. And we're also going to look at the implementation of the QPE on that 4x4 matrix, which we had in the first project. And we are going to look at the stability of the algorithm and how many qubits you actually need to get a specific precision. So these are things which we will go back and forth with. It means that when we look at the projects, you've probably seen that there are some suggestions. And one is actually implementing a QFT, quantum Fourier transform, and a QPE from scratch. And then compare that with what you did in project one. And then have a critical discussion of a method which in principle is not variational, like the QPE, and a variational method like the VQE, which is then based on a parameterized quantum circuit. I'm going to revise a little bit the project proposal, and I also know that many of you are also interested in other topics. So if you have things which don't match exactly what I have put in the list, I mean, please feel free to come with suggestions till the beginning of next week, because then we still have at least roughly 2 months to work on the project. So that was a little bit about some practicalities. That one. And just quickly, this algorithm simply solves this equation here, where A is a matrix, X a vector, and B a vector. The other algorithm, which we will discuss next week, the plan is actually to go through the QAOA algorithm, which stands for Quantum Approximate Optimization Algorithm. So the HHL and also this algorithm have strong links to machine learning and quantum machine learning. So I will try to expose some of these links as well. Now, one thing which I will not touch upon is actually the how you would implement real data, let's say from options in finance for the QAOA algorithm. So I will basically discuss the algorithms and how to implement them. But I will not say much about how you actually encode the data. That's largely also due to the fact that I am a differential equation person. And then it's pretty easy to actually encode the data which I want to deal with. So this is actually a variational algorithm. So all the algorithms we have looked at till now are variational ones. So in a sense, this leads to what we have called a parameterized quantum circuit. which is used then to search for good solutions to hard optimization problems. So we will discuss the mathematics of this one next week and also the week thereafter, when we will start with the quantum machine learning algorithms, because they link pretty well here. So that means that if we now look at the plans for this week is actually to both look at the implementation of the QPE and quantum Fourier transform. I will discuss the HHL algorithm and its implementation next week. And as you will see here, the kind of topic which I'm aiming at for the rest of the semester is to start discussing this algorithm today. We will sum up the discussions and also look at how we can code it. And my hope is to present an algorithm which solves the Poisson equation in one dimension, which is a pretty straightforward algorithm to implement by linear algebra methods. It's normally done by a very simple to implement algorithm, which is called the Thomas algorithm, which reduces a problem like the solution of that A times X. If A is an n times n matrix, this is typically something which requires n cubed floating point operations. The Thomas algorithm reduces this to a linear dependence on the dimensionality of the matrix. So obviously the HHL algorithm, the way we are going to implement it is not going to beat a classical algorithm like the Thomas algorithm for that specific case. Then we will try to discuss the QAOA, and we will link these with quantum machine learning. And if we get time, we will get started with the basics of quantum machine learning algorithms. And then we have one of the classic approaches, which you will encounter in basically every textbooks on quantum machine learning, is to link classical support vector machine algorithms with quantum support vector machine algorithms. And then we will dive into quantum neural networks and continue with that and look at some implementations. And then if we get time, I may say something about one of my favorite topics, which is about Boltzmann machines. And then finally, we wrap up that last week. This is roughly the plan for the rest of the semester. Any questions, suggestions, ideas? So give it a thought, and then feel free to come back with inputs, ideas, and thoughts about the project as well. Okay? So what I wanted to do now is to quickly bring up some of the things which we discussed last week. And last week we ended with the quantum Fourier, the quantum phase estimation, but I actually wanted to bring up some of just quickly remind you about quantum Fourier transforms. And as I said, this is like a kitchen item which enters quantum phase estimation algorithms and many, many other algorithms. And what I'm going to try to have you with me is a kind of chain of algorithms which enter other algorithms. So the HHL is based on the QPE, which is based on a quantum Fourier transform. So there's a kind of chain here of algorithms, quantum Fourier transforms of the basis, actually the inverse one for the quantum phase estimation. And then the HHL for solving linear algebra problem is based on the QPE algorithm, the quantum phase estimation algorithm. If you want to dive into Shor's algorithm, that is also based on QFT and QPE. And many other of the algorithms in quantum computing are actually based on these two building blocks. So I'm going to quickly remind you of the Fourier transform, if that's okay. And then we can look at how we can encode it. And then we go back to the QPE and look at how we set it up. And then we will look at some code examples as well. So let me stop sharing this one and bring up the slides from last week. So I hope you don't get offended if I remind you of some of the things we've done. But it's sometimes, since we had a break in between, it can be useful to actually remind ourselves of some small technicalities. So what we did the last week was actually to summarize the quantum Fourier transform. So basically, the quantum Fourier transform is, as it says here, it's one of the central algorithms in quantum computing. So you will find it in Shor's factoring, order finding, period finding, quantum phase estimation, and several quantum simulation algorithms. So it's a central, which I normally like to call is a kitchen ingredient, a kitchen tool, actually. So it's the analog of the discrete Fourier transform. But instead of, if you think of the discrete Fourier transform, and as we discussed last time, you can implement it in a brute force way, where the transform is simply given by this matrix multiplied with a vector x. So you can actually replace this component xj with just a vector, and then you would get a new vector y, which is given by this matrix, f of n, multiplied with x. That requires a lot of floating point operations, which are normally translated into a faster algorithm, which is called the fast Fourier transform, which goes like, if n here is a dimensionality, this goes like n times n log n floating point operations, if you do a fast Fourier transform. If you do this one, this is just like n squared floating point operations. And the quantum computing algorithm is actually something which requires much less floating point operations. But the quantum Fourier transform is equivalent to this one, except that now n here is actually 2 to the power of little n qubits. So the quantum Fourier transform is actually mathematically looks the same. So that maps a computational basis states to a coherent superposition of all basis states with the basis determined by this x here. So in general, this map is linear, and for a general state, this is actually what we have here. So the quantum Fourier transform acting on the state psi here is actually the same as this set of coefficients, where n minus n now is the number of configuration given by the qubits in a base of 2, 0, and 1. So that means that little n is a number of qubits. So this uppercase letter n is actually 2 to the power of little n. And what we did then was to use a binary representation of these integers. And we used a float representation. So I'm not going to go through all these details, but I just wanted quickly to remind you of some of the basics. So here you will find the basic derivation of the formula, which is encoded. So the standard Fourier transformation, quantum Fourier transformation, is now given where little n is the number of qubits, is now given by a set of operations which then can be transformed into Hadamard gates, controlled phase rotations, and a final qubit reversal which swap, given by the swap gates. But normally that is not implemented. So we went through several examples, but I just wanted quickly to show you a 2-qubit circuit where we had a Hadamard, we had a rotation gate, a unitary transformation, and then we had a new Hadamard, and then we would swap in order to reverse the qubits, unless we just keep the given order, and then we know exactly how that order should be used to swap. So that would be a 2-qubit circuit. And we had examples where we looked at the 3-qubit case. So then we would have a new Hadamard, a new rotation, and then a new rotation on this qubit. So these are all 1 and 2 qubit gates. Then we have a new Hadamard, a new rotation, a new Hadamard, and then a swap. So that's the basic setup of a quantum Fourier transform and the way it's actually implemented in the code which you have access to. So you would apply a Hadamard, and for each later qubit, you apply a controlled rotation gate, and this continues recursively, and at the end, you just reverse with the swap gates. So you have 8 Hadamard, control phases, Hadamard, control phases, and then till the end, the swap method. So a typical schematic pattern would look something like this. And then this would just continue till you have the final swap gate. And there are several examples here which we went through. And as I said, the QFT is used for the phase estimation, period finding, and also extracting eigenphases of unitaries. So it converts arithmetic structure into measurable interference structure. After the break, we're going to look at the codes both for the QPE and for the QFT. So in practice, many algorithms actually use the inverse QFT rather than the forward QFT. And actually, it's inverse QFT which is used in the QPE algorithm. So these are things which we went through last time, and I'm not going to repeat them. But the thing I wanted to say is that why these are important. It provides a mechanism for converting phase information into computational basis information. It exploits interference to extract periodicity, and it connects time evolution phases to measurable outputs. So it's a typical bridge between dynamical phase accumulation and algorithmic readout, which we will see more in detail today when we look at the QPE algorithm. So in summary, this is a repeat from last time. The quantum Fourier transform is the analog of the discrete Fourier transform. It factorizes into 1 qubit phase states, is implemented using Hadamard's controlled rotations and swap gates, and has a complexity which goes like the number of qubits to the power of 2. And it's central to many, many other algorithms. So let's now look at the quantum phase estimation algorithm. And there is something which I actually wanted to say a little bit about. And I wanted to remind you of things which we discussed at the beginning of the semester. So if you look at this expression here, if you now look at a unitary operator, so how many of you have actually seen this expression here? Roughly, not everybody. So I'm going to give you some details behind that one before we jump into the QP, if that is okay. So I'm just going to derive that expression. I see that roughly 50% of you have seen it. So I hope you don't mind if I go through the derivation, because this is a central aspect of the quantum phase estimation algorithm. So the goal of this algorithm is actually to estimate this phase phi. Now, the problem which we are going to face is that we are looking at a Hamiltonian. So we would like to have the eigenvalues of a Hamiltonian. We are not interested in the eigenvalues of a unitary because they are equal to 1, the absolute value. But we would like to have the eigenvalue of a Hamiltonian, and we know that the Hamiltonian is not necessarily unitary, but it is Hermitian. That's an assumption which we are making about it. So let's just dig back a little bit and let me try to remind you of this relation here and how that comes through. Is that okay? So let's just go through some of this basic mathematics. So this is a small detour so that everybody actually has a clear understanding of where this comes from. So let me just switch to the whiteboard. So if we have a unitary operator, what we have, so a unitary operator here, that means that if I take U with its Hermitian conjugate, this is obviously equal to the identity matrix. And we know that U acting on this given state is given by E times 2 pi I of phi multiplied with psi. So this is not true for an arbitrary state. Keep that in mind. And it's true precisely when psi is an eigenstate of U. So keep that in mind. So if psi is an arbitrary state, not an eigenstate of U, then this is not true. So let me just write it. So true if psi is an eigenstate of U. So if that is the case, what we then have, if that is true, then we know that this has to be obeyed. So lambda is an eigenstate of psi. And we know that for a unitary operator, then we must have lambda, the absolute value, equal to 1. So that means simply that lambda is equal to e to I of phi of theta for some real theta. So let me just show that one to you so that you see that that is the case. And we have said that U is unitary. So that means that if U acting on psi is equal to an eigenvalue times the eigenvector, then what we know is that if I take the norm of this quantity of U times psi squared, so this is the norm 2, then we know that this is nothing but the norm 2 of the vector, because this is a unitary, right? So what you get then, this is psi times U of U times psi. So that is simply just psi times psi, okay? But this is also, what we have is if I take the norm 2 of this quantity squared, this is actually equal to lambda times psi norm 2. So I'm just going to put the 2 here. And this is nothing but the eigenvalue squared times psi, the norm of the vector. And that clearly leads to, since psi times psi, the norm, we assume that this vector is orthogonal and normalized. So that means that this guy here has to be equal to 1. So that means simply that lambda, the absolute value, has to be equal to 1, okay? Now, since this lambda is equal to 1, that means that every eigenvalue quickly, so this is just a quick reminder of the basic mathematics here. Each eigenvalue lies on what we call the unit circle. Which means then that we have lambda of E of I of theta, and the phase is periodic. The phase is periodic, so theta is the phase, is periodic modulo 2 pi. So we know that just at E of theta plus 2 pi is equal to E of I theta. And then you may actually then write that theta is 2 times pi times phi. And this phi takes values between 0 and 1. And that's why we write this lambda is equal to E of 2 pi I times phi. Okay? So there's a little bit more here, which we need now as a background. So one thing which I wanted to is to remind you a little bit about the spectral decomposition, because that's one of the basic quantities which we're going to use when we set up the QPE algorithm. So if we now ask ourselves, what about a general state? So suppose now that we have a eigenbasis of U. So what we do now is that we let this basis uj be an eigenbasis. Then we are going to use the spectral decomposition to express another state and another operator in terms of this eigenbasis. So we assume that this is an eigenbasis of U. That means for a general state, what we are going to have then, we're going to have a general state psi is something which we then can expand in terms of this basis of uj's. So that means that if I act with U on psi, this is the same as J, and then Cj, and these are eigenstates, and then e to the power of 2 pi of I of phi j multiplied with U of j. Now, you note one thing here is that you cannot factor out a single phase unless all the occupied eigenspaces carry the same eigenvalues. Okay, so that's just a small additional property here. But the thing which is now interesting for us is actually the spectral theorem. So let me quickly remind you of that. This is something which we defined in the very beginning of the semester. So the spectral theorem and we should add here that I'm just going to deal with the spectral theorem in finite dimension. So there is one for the continuous or the infinite dimension, which you would typically use when you represent, let's say, momentum, position, etc. But we are going mainly to deal with a finite number of qubits. So that means that in essence, our space is going to be a finite dimensional space, which is defined by the number of qubits. So we don't need to look at the continuous variant of the spectral decomposition theorem or the spectral theorem, okay? So we have already seen that one because we know that when we have this basis, so we have U acting on this uj, so these are the eigenstates. So we have E over theta j multiplied with U of j. So what we can do then is actually to rewrite U in terms of the spectral decomposition where we have the eigenstates, also the eigenvalues, sorry. And then we have the outer product, which is defined by the eigenbasis which we have. So that means that the spectral, you remember we have the eigenbasis, and then we have the eigenvalues, and that allows us to define the spectral decomposition of an operator. So we know that this now is given by J of E of 2 pi I of phi j multiplied with uj and uj. Okay? So we saw that in the very beginning of the semester. So this holds actually because we have a unitary operator. We could also rewrite this in a form which we saw earlier, where we wrote it like J times a lambda J and multiplied with a projection operator. And this operator Pj, well, let's just, Pj is simply given by uj, uj, and lambda J here is simply E of theta j. So what we typically say then is that this P of j projects onto the eigenspaces, which are defined by the basis and corresponding to a specific eigenvalue. So as I said, I'm not going to look at this in infinite dimensions, but I wanted to say something why this matters. So these finite dimensional spaces which we have here, they are typically the spaces which we deal with when we deal with qubits. So the infinite dimensional variant, which we haven't touched upon over the spectral theorem, this is something which you would find for position, momentum, quantum fields, wave equations, etc. But these same principles, they actually survive when you have unitary operators, also multiplications by phases in the appropriate spectral representation. Now comes the problem. And when we are going to look at the quantum phase estimation first, we are going to look mainly at how to obtain this state phi j, or this value phi j. But in our case, we are going to deal with a Hamiltonian, which is not unitary. So in our case, we will be interested. So the QPE algorithm actually deals with how to find this to a given precision. Okay? But then you may ask yourself, how do we link this with the eigenvalues of a Hamiltonian? So in our case, we will, no, not will. We are interested in the eigenvalues of a Hamiltonian H, or an operator. Let's just call this in more general terms, an operator A, which is not necessarily unitary. So that means that everything we've showed till now may not be used. I just say may, which means that it actually can be used. But which is not necessarily unitary, but we assume that it is Hermitian. We assume it is Hermitian. So the typical time evolution which we are interested in, what we have then would be something like A times some state psi, and then we have some eigenvalue A times psi. This is often the problem which we are interested in. So how could I use now these unitary operators? Because this A is not necessarily unitary. So the Hamiltonian of a given system is not. So if I would like to simulate a system now and still use these properties of unitary transformations, how could we actually do that? So any good suggestions? So we could actually look at the time evolution, which is generated by a given Hermitian operator. So the time evolution which is generated would then be given by u of t, and that's given by e of minus I times a times t. This is a unitary operation. So that means that if I now look at if we have the system with A multiplied with psi is equal to some, let's just put some I here. That is equal to A of I times psi of I. What we will have then is actually the following, that this u of t acting on this psi of I is then going to be given by e of minus I times ai times t multiplied with psi of I. And this is the quantity which we are going to look at. So that means that you can also make a spectral decomposition. So if we look at this operator, u of t, which is e of minus I times a times t, this is something which we then can rewrite in terms of a spectral decomposition as e to the minus I ai of t, and then we can expand it in this basis which we have. So this is j and u of j. So this u is the eigenbasis of u. So that quantity which we have here, this one, that's normally called a dynamical phase, which is being accumulated by the eigenstates u of j. So the eigenphases are the unitary operators. They encode the energy spectrum of the operator A. So the QPE, when we look at that one, and this is a transition to the algorithms. So the QPE begins with the relation where we have a unitary operator acting on uj equal to e to the power of 2 pi I of phi j multiplied with u of j. And the goal is to estimate this phi j. So what are the basic ingredients? And we are going to come back to this when we look at the algorithm details. So why does it work? Why QPE works? So it has basic ingredients. So the ingredients of the algorithm are: one, an eigenstate of uj. They're going to be controlled powers of rotation gates. I'm coming back to this when we are going to look at things in more detail. And then finally, there is an inverse Fourier transform. So one of the points here is that if I look at the operation of a control gate of 2 to the power of k, so this is k is a qubit number k, and when this acts on u of j, this is going to be equal to e to the power of 2 pi I, 2 to the power of k times phi j, acting on this u of j. And the phase is actually imprinted on the control register in a binary form. So if the input is not an eigenstate of a unitary operator, this is important actually. If the input is not an eigenstate, what happens then? Then what we would have then is that we can always expand a state psi in terms of the basis which we have of uj. What the QPE does then the QPE, what it does, it produces a chain of CJs, and we have a phi j multiplied with this uj, so that the measurement outcome sample one of the eigenfaces with a probability CJ squared, so that the measurement outcome that samples one of the eigenfaces with a probability which is given by the CJ squared. So the other thing which we actually want to is to now try to link with a given Hamiltonian the eigenvalues here, which we get, or the eigenfaces which we get from the QPE algorithm. So what I'm going to do now is to switch a little bit back to the slides and bring up those slides which we had last week or the week before the break, and then look a little bit more into the details of the QPE algorithm and how we would implement it. So basically what we are using is the spectral decomposition that plays an important role in the QPE. Now, with the spectral decomposition, we can then find this phi i's, these phases. And when we have these phases, we can then extract the eigenvalues. Because if we now look at the eigenvalues, if we now use the fact that we have a Hermitian operator, so suppose now that we, just let me give you that as a kind of a small item here, because if we have U, which is given by, suppose now it's just given by I times A times T, so A is Hermitian, then we know that E of A of T acting on U of J is then given by E of I of lambda J times T multiplied with U of J. And the eigenfaces then are phi of J equal lambda J times T divided by 2 pi. So when we have this phi J's, when we have estimated them from the QPE, we can then extract the eigenvalues, lambda J's, of this operator A. So you can put a minus in front here and you just have a minus there. So this is a unitary operator, what you have here. And this is the way you would implement it. And then when you have found this phi of J's, then with a given time here, you simulate up to a specific time, then you can extract lambda J's simply by taking the value you found. You have 2 pi and the value of T here. But let's try to go back to the PDFs from for this week and take a look at how we would set up the quantum phase estimation algorithm. What you see here is actually also the core of the HHL algorithm. So keep in mind that so let me just mention this as an aside. This is also the basis of the HHL algorithm. And in that case, and we are going to list this after the break, we have an equation where we have a matrix A. So this matrix is assumed to be Hermitian. It also has some other properties we want it to obey. And one of these properties is it's a sparse matrix, which is also the case if you're solving partial differential equations. B is a known vector, and X is the unknown quantity. So this equation, which we are going to use in order to find these eigenvalues, is something which we are going to use again in this equation. And I will try to sketch how we actually find the solution to this equation here using the eigenvalues we get from the quantum phase estimation algorithm. So the HHL relies on us being able to calculate these phases by the quantum phase estimation algorithm, because what this algorithm is doing for us is actually that it's going to attempt at solving this problem. So then we need the inverse eigenvalues. So this is the basics of the quantum variant of a linear algebra problem. So we are coming back to this, but first we need to go into the QPE algorithm and look at how we can implement it ourselves. And then we will show you through the Jupyter notebooks, which you have access to, how you could actually implement the QPE and study its dependence on the number of auxiliary qubits, or ancilla qubits as they're called. But let's now switch back. Any questions, by the way? So I wanted to give you some of this basic mathematics because that links the quantum Fourier transform we are going to look at, the QPE, with the HHL algorithm. We don't need to talk about the HHL if you're not interested in that problem, but the QPE itself is a central ingredient because it allows us to find the eigenvalues of a given quantum mechanical system, for instance. If you're not interested in the eigenvalues, if you have a unitary operator and you're interested in the phases, then this allows you to estimate the phases. So let's go back to the slides which we went through last time, but which are also the core of this week. So let me just find the preview here. Okay. So we took a long detour here And wait a moment, I think, let me just stop sharing again. I don't think you online see this. Let me see. Yeah, let me just go away from that one. And let me try to share again. Here we are. And let's take the full screen here. So what we did now was a long detour to give you the background for the expression which you see here. Okay? And as I said, I mean, sometimes it can be useful because one of the reasons why I wanted to remind you on how we can actually use, how we get this expression is also the fact that we need the spectral decomposition, because that's a central element when we set up the QPE. So I see we are a little bit over time. Should we take a small break? And then after the break, we go through the QPE algorithm. We look at examples, and then we go back to the HHL algorithm and its derivation. Okay? So let's take a small break. So the QPE has been one of the central algorithms in quantum computing, and it was used to estimate energies in many-body problems, quantum chemistry in particular, simulating Hamiltonians, and also when it comes to Shor's algorithm, if somebody's interested in that as a variant for the second project, this is something which is a very viable project, but it's can be difficult if you are not too familiar with the number theory. And as I said before the break, if you can encode a Hamiltonian into a unitary, and this is what we did with setting up the exponential of the Hamiltonian, then the QPE can extract the eigenvalues. And this is what we are going to look at now. So I wanted to give you roughly the algorithm first, and then we are going to break it down in some simpler examples and look at how we can implement it later as a code. So the whole thing is, if you want the eigenvalues of a Hamiltonian, and this is, as I said, a viable alternative for the second project to implement your own QFT, your own QPE, and make a comparison with the variational quantum eigensolver which you developed in project one. So if you can encode the Hamiltonian into unitary, which is done through the exponential, then QPE can extract the eigenvalues. So I want to bring in some namings here. So you actually use something which people call registers, or we split between systems and ancilla qubits. So we have something which is called a control register of n qubits, which is typically initialized as a tensor product of bit zeros. Then there is a system register, which is initialized in a given eigenstate. So that means that the initial state of the system is given by this set of initialized states times this eigenstate of the system, which is the one we are interested in. So the control register, that's the one which stores the estimated phase bits. So let's take a look at a simpler case here of what is going to come. So I'm going to switch back a little bit to the whiteboard and just look at a very simple system. So keep this in mind. You have two registers. So one which contains a given number of qubits, which are initialized as zeros. And then you have a system register, which then is initialized in the eigenstate phi of the system. So let's go back to the whiteboard just for the example which we're going to show now. So when we look at the QPE algorithm, I want to introduce some of the basic names. We would typically initialize the system. So we have a basic recipe. One is to initialize n bits in the state 0. So that means that we would then have a set of tens of products of these different zeros. And we would typically write this as 0. And you've probably seen this notation several times. So this is a tensor product of all these qubits. So these are normally also called ancilla qubits. And these are the ones which are going to give us the phase. And from the phase, we can then extract the eigenvalue of the system we are going to look at. So this is normally called the also the control register. So we initialize this system. This is often called a control register. And then the second register is the one which then contains the state we're actually interested in the eigenvalue of. So second register. And in some textbooks, this is just called the system we are interested in. That contains all the qubits which are needed to define a given state, all qubits which are needed to define the state psi. So let me try to show this kind of basic recipe by just using one qubit in the control register and see what kind of type of operations which we then can use in order to get the information about this specific phase. So let's write down the first operation. So we have this qubit 0. And we are going to perform a Hadamard on that one. So our initial system contains now the system, or the second register, as we called it. So the initial state is the tensor product of these two guys, which we often just write like 0 of psi. But when you see this second notation, this actually is the tensor product of these two states. So this will be the first operation, which we are going to do now. This is the Hadamard. And let's now just call this for a psi1. So it means that the state psi1 is simply now going to be given by a Hadamard acting on the first qubit, this ancilla qubit, as it's also called, of 0, tensor product with psi, plus 1, tensor product with psi. Okay. Now, the next operation is an operation which is going to be given by a controlled U, a controlled rotation. So we're going to set that one up here. And that gives us a new state, which I'm going to label as a psi2. So that is now a controlled U operation. So that has a rotation here. So it means that this state psi2, when I act on this with this gate, this is going to give me 1 over square root of 2, and then nothing happens to the first qubit, because this is a 0 state, but it's the second one which gets changed. So that will now have E of 2 pi of I, And since I now have just one qubit, this is now given by this representation here, which is the binary representation. If you think back of the rotation, this operation which you see here, so this is 1, and then tensor product with psi, like that. So when I have the rotation with only one qubit, so let me quickly remind you of this specific notation here. So we have 0 of phi 0. This is the same as the value of phi 0 multiplied with 1 over 2. Okay? And phi 0 takes the values 0 and 1. So this is basically what we did as well when we now set up the quantum Fourier transform. We had this specific notation here, and in case of just one qubit, we would then just have phi 0, and phi 0 could be 0 or 1. Okay, so this is now just another way of writing the unitary transformation with this controlled U gate acting on 2 qubits. Okay, so if I write it out, then I can write it in a more compact way. So this will be given by 1 over square root of 2, and I have 0 plus e to the 2 pi of I of 0, pi 0, acting on 1, and tensor product with psi here. The next thing I can do now, so this is the state psi 2, then I can have a Hadamard again. On psi 2. And if I do that one, this H on psi 2 here, this gives me a new state, psi 3. So if I just write it out again, I have a Hadamard here again. And then I end up with a new state, which is my state psi 3. Now, this state psi 3, if I now put everything together, this is actually going to look like as 1/2, and then I have 1 plus e of 2 pi of I of 0 of phi 0 multiplied with 0 plus 1 minus, because I'm implementing the Hadamard operation, on 2 pi of I of 0 of phi 0 multiplied with 1 and tensor product with psi. So what I do now next, if I now measure on qubit 0 or qubit 1, so if I perform a measurement, so I measure on 0 or 1, then what I would have is that phi 0 is either 0 or 1. So what happens then is the following. So if phi 0, because these are the values which we have opted for, so if phi 0, if phi 0 is equal to 0, then the state psi 3 is equal to qubit 0. If phi 0 is equal to 1, what happens then is that the state psi 3 is equal to qubit 1. So if we measure with certainty, with a given certainty 0 or 1, then phi 0 is equal to 0 or 1 times 1/2, which is equal to 0.5. And when we do that, we know then the value or the phase, since this of the eigenvalue. We know the there is a missing word here. We know the eigenvalue. Since this eigenvalue is now connected with the e to the 2 pi I times phi. Now, the problem which we have here with only one qubit is that our precision gives us only two values, either 0 or 0.5. So with only one qubit only, we have either 0 or 0.5. So there are only two possible values. So if the actual eigenvalue is 0.25, we will not get the correct value. So if you choose two qubits, with two qubits, then what we would have is 0 and phi 0 and phi 1, which means again then that if we do that case, then this translates into phi 0 times 1/2 plus phi 1 times 1 divided by 4. And both of these guys here, phi 0 and phi 1, they take the values between 0 and 1. And that means that the final phi, which we then can define, can be either 0, if both are 0, or we can find 1/2, if one is 0 and the other is 1. That means phi 0 is 1 and phi 1 is 0. Alternatively, we can get 1 divided by 4, but we can also get 3 divided by 4. So that means the more qubits I have, the higher the precision of the value phi. So if I have only one qubit, there are only two possible values which I can get, which are either 0 or 0.5. So if those are the exact eigenvalues we are looking after, we are done with only one qubit. But in general, we know that the values we are looking after will not just be given by these numbers, which are exactly represented by a binary float representation. So let's try to go back now to the PDF file and take a closer look at the basic algorithm for the QPE. Oops, sorry. No, not that one. So the example which I showed you was an example with only one qubit, and you could expand this to 2 qubits. But the basic idea now is that by setting up this control register, as we called it, alternatively, we could call it just the ancilla qubit, but the control register is a well-established name, and then we have the system register. So the initial state would now just be given by the tensor products of these initialized n qubits and the state, which is an eigenstate of the system we are interested in. And this control register stores the estimated phase bits. So you would apply Hadamard gates to all control qubits. So that means that the total state, so this 2 to the n, this is actually a loop over all the possible configurations we have, all the possible states which can be realized. And by the Hadamard gate, so we have a superposition of all the control qubits which are initialized to 0. So that's the first operation. And if you go back to the drawing which I made for just one qubit, you saw that we had a Hadamard there. That means that the total states is now simply given by this tensor product between this linear superposition, which is the state psi2, which we had, no, sorry, psi1, which we had in the one qubit case. Then the next step is to apply control powers of these unitary transformations, which actually the rotation gates, and they will be given by the first qubit, the second qubit, and etc. And each control qubit determines whether the corresponding power is applied. So because this psi is an eigenstate, what that means is that when I apply this, this should behave like this expression which we have here. So each control unitary writes phase information into the control register. Keep that in mind, the control register. So the state after these control powers, if the control register basis state is K, then the controlled operation U of K gives us this. And you can extend easily that one qubit example, which we showed on the whiteboard. And that means that the combined states becomes this expression which you see here. And what you will see when you look at this one, this looks very much close to what you've seen with a quantum Fourier transform. So the system registers factors out. And if you go back to this example with the one qubit case, tensor product with the state psi, if you look back at the notes we had on the whiteboard, you will see that this is exactly what happens, is that the system register actually factors out. And the control register now contains the phase information, as you saw for the one qubit case. And you can easily extend that onto 2 qubits and more qubits. And then the control register is in this specific state, which is nothing but a Fourier type of transformation. Nothing but that. So that's why, because we want these guys, this is what we want. And that's why the inverse quantum Fourier transform is actually the next step. So it converts the phase-encoded superposition into a computational basis approximation of this phi. So if you look back at this one qubit case we had, you can now see that what we did there was simply to run through with a Hadamard and a controlled U-gate. And you saw that the states did separate. The information about these phases are kept in the control register. And we can then, by an inverse Fourier transform, we can then get the phases phi. So when you apply that one to that control register, this is essentially what we end up doing. This is just the inverse Fourier transform on the states here. Then we can extract this phase phi. If this is given exactly by the numbers we had, so for the one qubit case, we had 0 or half. So if this numbers here can be exactly represented, this number phi, for some integer n. So if we have one qubit and the values we are looking after are either 0 or 1/2, then we have an exact representation with one qubit. If we are, on the other hand, have 1/4, we would then need 2 qubits. Or 3/4, we will still need 2 qubits. If we have more complicated values, we would need more and more qubits. So what we are playing around with is actually the binary float representation of a number. So so if we have some integer n, this simply becomes the state n we are looking at. So the control register stores the exact n-bit binary expansion of this phi here. And that's the whole trick with the control register. So if you have this one, this is what we typically, the way we would encode a set of bits. Then after inverse QFT, the control register becomes simply phi1, phi2 up to phi n. So that gives us these different coefficients phi's. Then measuring the control register. So if I do like I did for the one qubit case, if I make a measurement either on qubit 0 or qubit 1, then that returns the exact binary digits of phi. So let me quickly go back to the what we did with the one qubit case. But sometimes the one qubit case is maybe too simple. but in this case here, it actually shows you what is taking place here. So if you look back at what we did with just one qubit, so we set up a Hadamard transformation, and that gave us a new state phi1, which is this one. And then we performed the control U operation, which is an operation which acts on these two states. But what we saw then, when we simply now just have one qubit, we have only phi0 here, and phi0 takes the values 0 and 1. And that means that I can have, if it's 0, then this obviously becomes 0. If it's 1, it becomes a half. So that's the only information I can extract here. Oh, because these are the bits which you have chosen. This is the bit representation. So you can have, if you have a binary system, we are assuming a binary system here.
And the problem is if we want you, sorry.
Yeah. That could happen. That could happen indeed. Yeah. But the thing here is that when you look at this operation, it actually separates. So you can, so the whole thing just applies to the controlled qubits. And so that means that when you now operate on this one, the way the mathematical structure here is so that when you look at it, you can separate out the control qubits and the system qubits. And when you have separated it out, then when you make measurements now, so you can perform a new Hadamard if you want to, when you make measurements, then you project out either 0 or 1. And then by the inverse Fourier transform, you can then extract phi0, which is the one you want to have. So if we go back to the, it's always useful when you look at these algorithms to look at a case where you can do the mathematics. And in the case of the QPE and also the QFT, to do this for 1 qubit and 2 qubits is often the simplest case to set up by hand. So as soon as you have found with inverse QFT, you actually find the control register. So this is the set of qubits which you have, the values of the bits 0, 1, 1, 2, etc. And then measuring the control register returns the exact binary digits of phi0. And that's essentially what we did with the other case there. So if you can show that the control register state after control powers, you can actually show this. It factorizes like this. So that means that you would then have something which really looks like a standard quantum Fourier transform. So each qubit which you have then encodes actually one successive binary suffix. So using this one, the control register state becomes given by this one, and which has exactly the structure of a quantum Fourier transform. And that means that when you apply the inverse one, that yields this bit string here. Essentially, the way your circuit is going to look like is something like this. So these are these different powers of the unit of the rotation transformations, and you have the Hadamards and all the qubit, the control qubits. This is your state psi. You perform these unitary transformations, and then you have a inverse Fourier transform, and then you make the measurements on each qubit here. So this is roughly the circuit which you would get for a quantum Fourier inverse transform in order to get the eigenstates. So in case your value phi is equal 5 divided by 8, then you have an exact representation in terms of these bit values here. So then the ideal QPE output on a 3-qubit control register is actually 101. And if you look at that one, you will see that the eigenvalue which you're getting, or the phase phi, is actually 2 pi I of 5 divided by 8. So after the control powers in inverse QFT, the control register collapses to this bit string 101 with a probability 1. So this is an example of where your phi can be exactly represented by only 3 qubits. In case you had 0.5, you would just need 1 qubit. If you have 1 divided by 4, you would need 2 qubits. And this case here is a case where with 3 qubits, you get an exact representation of this value phi with 3 qubits only. Now, this is the standard case. Normally, you never have an exact representation in terms of a finite number of bits. And you know that if you take a number like 0.1, 1 divided by 10, and if you try to represent that one with 10 bits, you will not get an exact binary representation of a decimal number 1 divided by 10. So you would need actually an infinity of bits in order to represent 1 divided by 10 exactly on a classical computer. And the same applies also to the quantum phase estimation algorithm, is that you will only have an estimated value with some type of error. So the output is actually a probability distribution which will be peaked near the best n-bit approximation. So this is what the QPE actually promises. And the measurement outcome gives the nearest binary approximation with high probability. So that means that the precision of the QPE with n control qubits, then it roughly has an approximation error which goes like 1 divided by 2 to the power of n. And that means that the precision improves exponentially with the number of control qubits. And this is actually one of the reasons why it has been so powerful. However, you see that the length of the circuits, if we go back a little bit to the circuit here, the more qubits you have, the more precision you want, the lengthier the circuits. So if you think back to the VQE algorithm, the length of the circuit was actually not that long. The type of operations which we did, we could obviously have many Hadamards and rotations on the qubits, but we could actually get away with pretty shallow circuits. Whereas when you implement the QFT and the QPE, the length of the circuits, depending on the number of qubits, can become pretty long. And that is one of the reasons why the QPE has, in a way, is less used in eigenvalue estimations than the VQE, which you tested in project number 1. So if you want the Hamiltonian in the system, and one of the big problems, as we said, is actually that the Hamiltonian is not unitary. And that means that we need now to rephrase it in terms of a unitary operator. And this is typically the type of approximation which you would use then by defining the unitary operator in terms of the Hamiltonian. And then you would act on the state with the unitary transformation. And then you would compare that one with the state which you get here. And then you would identify this phi in terms of the eigenvalue times time divided by 2 over pi. So the QPE can estimate energies if we can implement this unitary operator here. And this is the way you would typically do that. So if we want to connect this with Hamiltonian simulations, so the QPE requires controlled applications of this controlled U gates, which means essentially that this is the number of operations we need to include. So the QPE depends directly on the ability to perform Hamiltonian simulations. So there's something which we haven't discussed, which we will probably mention a little bit later, is actually the way we set up these exponentials. And that leads to something which is called a Trotter-Suzuki decomposition, which we haven't discussed. And there are many other ways of actually implementing the QPE efficiently for eigenvalue simulations. The physical interpretation. So QPE measures the dynamical phase accumulated by an energy eigenstate and the time evolution. It turns the phase into a bit string encoding the energy. So you can view the QPE as a highly precise, in a way, interferometric energy measurement protocol. That's the kind of physical interpretation you can actually give to it. It's important in many-body physics, and quantum chemistry has been one of the big fields of applications of many-body methods. It's a natural route to look at ground state energies. You can also use excited state energies and other properties of many-body systems. If we look at the connection to the VQE, and these are also things which we discussed last time. So both of these aim at a similar physics goal. So the VQE is variational. It's a hybrid quantum classical, and it's optimized by minimizing. And it's since the circuits are not that long with the VQE, it's actually suitable for present-day quantum computers. And this is one of the standard algorithms which people typically implement. The QPE, on the other hand, is fully quantum. It suffers from not being variational, but because we are making truncations to the exponentials often with the Suzuki-Trotter expansion, requires coherent control time evolution. It provides direct eigenvalue estimation, and it's actually best suited to fault-tolerant quantum computers. So the way they often are used together, this is actually a kind of strategy, and it could be a strategy for the second project, is to use a variational method such as VQE to prepare a good approximate state with large overlap with a true eigenstate, and then use that state as an input to the QPE, and then the QPE then refines the energy estimate to high precision. So you can actually use the VQE state which you get as an ansatz in the QPE calculations. Yeah, and we're just going to skip that one. So if you look at this in comparison, so the VQE often leads to shallow circuits. There are many repeated measurements. It has a classical optimization part. It's noise tolerant, and it's obviously limited by the optimization difficulty. And one of the things you probably saw in project one is that you needed quite many shots to get a decent estimate of the energy. So, and the optimization part in the VQE depends also on how you optimize. So if you just do a brute force gradient descent with a learning rate, which you have to fix, multiplied with the gradients, even if you use the phase shift rule and had exact expressions for the gradients, it was still dependent on the learning rate, which you had in the optimization part. So these are all kinds of pros and cons of these methods. The QPE, on the other hand, needs actually pretty deep coherent circuits. It requires a controlled operation here, which you have to approximate in some way or the other one. It can be very precise. It's ideal for quantum computers with which are fault tolerant, and it's often viewed as a long-term gold standard for energy estimation. But due to the fact that you cannot allow yourself to have very deep circuits, we often end up with a compromise between the VQE and the QPE. So these kind of things which you see here can actually form a basis for the second project. So before we jump into the HHL algorithm, there's a summary here. I just wanted to say something about the, I wanted to repeat some of the suggestions because I want you guys to start thinking about what you want to do in the second project. So one of them is obviously the implementation of adaptive VQE, and then run these on actual quantum computers. That will be a continuation, a direct continuation. There is another direct continuation of that project, which I think I had here. Yeah, that is implementing and comparing the quantum phase estimation algorithm with VQE. So that's also a very viable second project. The other ones deal more with an implementation of the HHL algorithm, which needs the QPE as a building block. We are going to discuss now the HHL algorithm, start scratching the surface of it. And then we are going to look at the later next week at the quantum approximate optimization algorithm. And then later quantum computing, quantum machine learning algorithms. But for those of you who are interested in continuing along the path of Project One, this is a pretty obvious one with adaptive VQE. And the other one is actually to implement and compare the quantum phase estimation with the VQE. Okay, I wanted to show some results from the codes actually before I jump to the HHL. So most likely I will start with the HHL next week because I wanted to actually get started to say something about the codes. And I see that I have been a little bit slow today. I actually spent more time on the, so I actually wanted to say something about the quantum Fourier transformation. So the Jupyter notebook this week, there is an explicit notebook which looks at both the QFT and the QPE and uses the QFT in the QPE. There is also another notebook, which should, no, not that one, but this one, which implements the Lipkin model with the VQE. But I will not discuss that one. But let's go back to the QFT VQE. So this contains, the first part is just the quantum Fourier transform as we have been discussing it. And that contains Hadamard gates, the phase rotation, and the swap gates for bit reversal at the end. These are the ingredients which are encoded here. And there is a Pauli decomposition also because we are going to have a Hermitian matrix, and that can be decomposed in terms of coefficient times the Pauli matrices. And then the quantum phase estimation algorithm uses the inverse Fourier transform. So this has a set of Hadamards acting on the qubits. So each qubit is acted on with a Hadamard, as we discussed in the lectures. We have these rotation gates, the controlled unitaries, and then we have the inverse, this IQFT is the inverse Fourier transform. And that gives us the basis states which we are interested in. And the phase then is given by this J, the encoded states, divided by 2 over T, where 2 over T is the number, T is the number of bits which we have, qubits. And then the precision is given by the exact value we want to reproduce minus J divided by 2 over T here. And that's the precision which we, for the eigenvalues. And in this specific case, I have a 4x4 matrix, which I diagonalize. And I compare that with the QPE. And you will see then that the different calculations give you, depending on the number of ancilla qubits or in the control qubits, number of qubits there, you will see that you will get slightly different results. So in here, I have an analytical QFT. So this analytical QFT simply sets up the matrix. So it's a brute force matrix times a vector calculation. That's the analytical QFT. So it's not me setting up an analytical expression, but it's actually me encoding the matrix elements of a Fourier transform as a discrete Fourier transform, period. And there is also an analytic inverse QFT. So, and you see that one takes the analytic QFT and just takes the conjugate. So that's pretty easy, okay? So this is nothing but a case where I just take a 4x4, which in my case now means that they have 2 qubits, so 2 to the power of 2. And it simply sets up the matrix, and it just tests that the when I take the Fourier transform and take the Hermitian, multiply with the Hermitian conjugate and subtract with identity, you see I get the 10 to the minus 15. I take the difference between my inverse QFT and the QFT transposed here, and that is basically 0. So that means that it passes the test. It also visualizes the QFT matrix, and you can now look at the different matrix elements. I mean, this is not that interested, but then I've set up the quantum Fourier transform. So this actually implements everything as a quantum Fourier transform, as we discussed. So, and the test here is actually again done for a 4x4 matrix. And you can see now that my, after I've done the QFT, this is the input state. So I have a 4 qubits. So that means that my matrix is dimensionality 16 times 16. And when I then have an input state, which is state number 5, and I perform the QFT, I see then that the norm is equal to 1, so that is correct. And I also test the difference between the inverse QFT and the Hermitian conjugates. You can look at these codes if you want to, and you can see now that the gate circuits QFT, this builds the QFT by composing Hadamard, controlled R-key, and rotation gates and swap gates. And yeah, you can take a look at these codes if you want to. And this could be useful if you want to make your own quantum Fourier transform and your own QPE algorithm. And you can see the tests here which pass as well. So in this case, it's with 3 qubits. So that's an 8x8 matrix. And you see now that the tests are passed to numerical precision. And you can see it's not so interesting. The thing I wanted to show you, and I see that my time is running out, so I'll pick this up a little bit next time. But there is if you run the QPE algorithm for this specific case here, this is just the implementation of the QFT, of the quantum phase estimation. This result here is a result which is now based on me using 10 ancilla qubits. If I have 6 ancilla qubits, my precision would be 0.098. If I take 10 ancilla qubits, you will see now that the difference between the quantum phase estimation algorithm and the exact one is at the level of 10 to the minus 3. So this is what I get if I have 10 ancilla qubits. If I now choose to reduce this one to, let's say, 2 qubits, you will see that this actually changes dramatically now. So let's just do that and run the QPE. So it's going to be fast, but you see now that the QPE error with only 2 qubits. So when I have 10 qubits, 10 ancilla qubits, my error was 10 to the minus 3. When I had only 2 ancilla qubits, you see my error is 10 to the minus 1. And this goes back to the phase estimation, because now with only 2 qubits, I can only represent 4 numbers. 0, 1 divided by 4, 3 divided by 4, and 1/2. So that means that in this particular case here, with only 2 qubits, my QPE is not doing too well. So you need actually quite some qubits. So if I switch now to 4, so let's just rerun it and just do that as the last case here. And now you're going to see it takes a little bit more time, but still, now the error is 10 to the minus 2. So with 10 ancilla qubits, I was down to 1 times 10 to the minus 3. And I was getting pretty close to the exact values. So the depth of the circuit obviously increases the more ancilla qubits I have. And if I bring this back to 10, as was the case, so with 6, this is the precision I would get. So this is the eigenvalue, 2 pi divided by 64, which would be the precision I would get with 6 qubits. So if I bring it back to 6 here, it's still going to take some time. And you see now it's going to run a little bit longer. And you would now see it. Let's see where the eigenvalues are. Now we are down to 10 to the minus 2 roughly. So with 10, which takes a little bit more time, you're down to 10 to the minus 3. Okay, I misjudged time a little bit. I'm sorry for that. I wanted to actually start with some of the basics of the HHL algorithm. You will find a lot of the information in the slides, but I will start next week with the HHL. So I needed a little bit more time to the QPE now. I'm sorry for that. Okay, I'm going to stop here.